I will try record it to the local machine. Then let me see. Oh, I just going to use whiteboard first. Okay, so today what we will discuss is another new concept, and this part of the notes, you can find it on sorting. Okay, so I put it in sort because it's more related. It's called Heapsort. Okay, but we first needed to understand the concept about a heap tree. Okay. Kind of so it's about a heap. Okay, and this heap is not the stack and the heap. Okay, not regarding memory. It's just some storage we try to use to a new data kind of structure to use to store, and it's also tree. Okay, but we will see the implementation. Previously we discussed binary tree implementation, use a linked approach, etc. And what we will see today for this type of tree is using array, or so array type. Okay, so array list or array to implement. But there is, if you do want to use array or array list to implement, and here the first concept we need to get it clear is called complete binary tree. And AVL we learn is called balanced, self-balanced. Okay, but this is another kind of a complete binary tree. Okay, so what that concept is, so there are some requirement is, the first requirement is non-leaf nodes must have two child nodes. So this we need to be careful. Okay, now must have two child nodes, and the leaf nodes. Leaf nodes must be filled. Here we need to be careful from left to right. So basically from left to first. When you fill the tree, okay, it's not a binary search tree, okay? So here we need to be careful concept. It's just a binary tree, okay, binary tree. Okay, so what are these two means? So we can take a look at a couple of examples, okay? So first, let's take a look. Like this, example 5, then 6, and 9, okay. Then we have 16, we have 11, and you have 20, you have 25. Is it? If we take a look, non-leaf node must have two child nodes. It's satisfied. And when we do the insert, you must insert from left to right. Must fill left first. Okay, must fill left. So that's so basically this is a complete binary tree. Okay, we can call this is a complete binary tree. And then let's take a look at another cases. So here I can use eraser. Then how about this? Is it so? If you take a look, this also follows the rules. This owns both property. So it is still a complete binary tree. Okay, so this is also a complete binary tree. And how about that? Let's get it back here. And let's get back the 25. And then I'm going to add something looks like this. So if it is this case, do you think it's a complete binary tree? The 7 go to right, not instead of left. So it doesn't fit this second rule, is it? Because leaf node must be filled from left to right. So then this is not a complete binary tree. Okay, so it doesn't meet the definition. So this is not. And then let's take a look more. Okay. Let me do erase. And 9, then let me draw like this case, 25, and then 20. Okay, and if you draw like this, then definitely this doesn't meet even the first condition. Is that first requirement? And so this is also not a complete binary tree. Okay, so for a complete binary tree, just try to make sure that both condition, both requirements need to be met. Okay, so that's the first condition that today we discuss. Complete binary tree. Complete binary tree. Okay, just remember the definition. And then next, let's take a look some features, okay, regarding the complete binary tree. So I'm going to draw the tree again. So 5, and then 6 and 9, okay, and then I have 16, I have 11, and then I have 20 and 25. Okay, so this is our complete binary tree. Then let me have something. So here we are going to have an array. Okay, suppose this is an array list in Java. Okay, or just an array. So we have 5 here, then we have 6, we have 9, then I have 16, I have 11, then I have 20, I have 25, okay. So I will also write down the index. So sub 0, sub 1, sub 2, sub 3, sub 4, sub 5, and sub 6. Okay, and then let's take a look. And with this complete binary tree, we can also see their level. So this is level 0. And then this is going to be our level 1. And then this is going to be our level 2, okay? So different levels. Oh no, level 0, level 1, yeah, level 2, yeah, that is right. Okay, I'm also going to write down the index, corresponding index here so that we can better understand, okay, and then 2. And then here it's 3 and 4 and 5 and 6. Okay, so this is regarding the tree and the corresponding array, okay? And within tree previously we learned that so 5 is parent node of 6 and 9, is it? And 6 is a parent node of 16 and 11, is it? And 9 is a parent node of 20 and 25, is it? So we have the parent node and child node relationship, is it? But let's take the relationship regarding the index. So the relationship of index of child node and parent node. Parent node. Okay, so let's see. And This is 0, is it? And this is 1. If I can rewrite it as 2 times 0 plus 1, is it? So it is what? It is 1, is it? And for this one, I can write as 2 times 0 plus 2, and it is 2, is it? So here is the parent node's index, is it? And then let's take a look, 3. 3, I can write as 2 times parent node, index is 1, plus 1. So this is 3. And the 4, it can be 2 times 1 plus 2. So it is 4, is it? And the 5, then you can 2 times 2, is it? And the plus 1, so it's 5. And here is 2 times 2, and the plus 2, so it's 6, is it? So if a parent, suppose parent, not parent, suppose just a node, okay, a node's index, suppose it is k, okay, then its child node, okay, child node, if it's left child node, the index, then can be what? Can be 2 times k plus 1. Is it based on, you see, the left child, it's all 2 times the parent and plus 1. Is it? Or 2 times something plus 1. So based on the parent node, is it? And the right child. Then the relationship is what? It's 2 times k plus 2. Is it? So that's the index relationship. It's an index relationship. And if you take a look here, is it? And because of the tree arrangement, so that's why we said you can use an array to store all of the items instead of we do the linked way, is it? So this is quite, we can say it's a kind of regarding how do you store to the array, it's quite straightforward. It's just based on the index relationship between a node and its child node. Is it a child node? Okay, and then on the other hand, if we know a node's index, suppose it's k, is it? And then how about its parent's index? Then the parent index can be what? You can do k minus 1 divided 2, is it? It's integer division, okay. So you can always have this kind of relationship regarding the index. Is it regarding the index? Okay, so this is we can store the complete binary tree. Is it using an array? Is it all array list? Java. Is it? But the concept is based, it's because of this special relationship. That's why you see, it said each non-leaf node needed to have 2 children. Is it? And the nodes need to fill from left to right. Okay, otherwise, you cannot get this kind of the relationship regarding the index, okay, regarding the index. Okay, so we understand the relationship between the index of a node and its child node, or a node and its parent node for the complete binary tree. So basically this kind of tree, we can also call it a heap tree. Okay, so that's the concept, and later on we will also see. And then let's see, then how do we kind of add some new item? Is it? Let's see the example. Okay, so let's go back to our original tree. So we have this 5, and then we have 6, we have 9, is it? And we have 16, we have 11, is it? And we have 20, we have 25, is it? And the corresponding array, let me draw it here. So we have 5, then we have 6, we have 9, we have 16, 11, 20, 25, is it? So sub 0, sub 1, sub 2, sub 3, sub 4, sub 5, sub 6. Okay, so now suppose I want to insert 7 to the tree. So how do I do it? Is it insert 7? Oh, and the one minor thing I forgot to mention is previously I just discussed complete binary tree. Is it? And when we discuss, generally when we discuss heap tree, we have either we call it minimum heap tree or maximum heap tree. Okay, and in this case, this is the minimum. Okay, the minimum, the concept is, if you take a look, is it the parent node is less than the child node? Is it always less than? And basically root node is minimum. Is it? And you can also reverse. Okay, you can also reverse. If you put like a parent node must be greater than the 2 child node, then it's maximum heap tree. Okay, so depends on you how do you arrange. Okay, so when we discuss like now we want to insert 7. So we are going to use the minimum heap tree, okay, to discuss all of our cases here, okay. And insert 7. So where are you going to insert? So basically, regarding the data structure, what it happens is you are going to add it at the back. Is it? So it's at sub 7 here. Is it? And you always need to fill left first. Why we say fill left first? Because you add at the back of the array. Is it? At the back of the array. But this is not a minimum heap tree. Is it? This is not. Is it? So how do we get it to a minimum heap tree? Is it? A minimum tree is its parent needed to be smaller. The values should be less than the child node. Is it? So what over here we can do is we can swap these 2 numbers. Is it? So you move 16 down, you move 7 down. Is it? You move 6 down, you move 7 down. Basically, in your array, you need to swap these 2 elements. Is it? So 16 here and 7 here. Is it? And this is still not minimum. Is it? So involve another swiping. Is it? Okay, so then you need to swap with its parent node. Oh, I'm sorry, that's not needed to use. So I'm sorry, that's already meet the, sorry. Okay, so here, So after we swap, so this is a minimum because it's less than the parent node, is it? So what we do this, you insert, is it? You insert and then you need to do what? You also need to move it to the location that it is supposed to be located, as it's supposed to be located. And generally we call this, because in this case, we go, whenever you insert, you always insert at the leaf node, at the very bottom layer, is it? And then it may involve you move up, is it? Swap up, is it? So we can call that called shift up, is it? Shift up, okay. And okay, so how about, so we have this one done. So how about let's consider one more, okay. So how about now you want to insert, so next let's do another one. Insert 0. Insert 0, where should I reinsert first? So who can tell me where I should go? Go to here, 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 here. So insert at which leaf node?
Insert in the back of the.
Yeah, here, is it? Yeah, here. Here is the sub 8. And the sub 8, who is its parent node?
Maybe we need to use the formula, like
yeah.
K minus 1 divided by 2.
Yeah, so this is 8 minus 1 and divide by 2. Is it? So 7 divided, it's 3. So you need to look for what? Sub 3. Is it? Sub 3. So who is sub 3? So from the tree, it's very clear. Is it? So you are going to insert it to its right. Is it? To its right. Okay, and after we insert, let me clear that out. Okay, after we insert, is this a minimum heap tree? It is not, is it? Definitely. We check bottom up. Is it? You start at the and compare with its parent. Definitely it's not. Then you need to do what? You need to swap. Is it? I need swap. So now I need to make 0 here and 7 here. Is it? So 0 go here and 7 go here. Is it? And then you need to what? You need to keep doing this. You need to check with its parent. Who is its parent? 6. Is it? 6, then you can find it's still not working. Is it? So you need to move 0 here and 6 here. Is it? So basically you're going to move 6 here and 0 here. Is it? So regarding array, then you just swap those 2 items. Is it? And then what? Then you need to keep checking with its parent. And the parent is 5. Is it? And we know you still need to do swapping. So it's 0 and it's 5. Is it? So 5 is here and 0 here. Now this is a minimum heap tree. Is it a minimum heap tree? Okay. And so from what we just discussed, you can kind of see, is it? You can kind of see that each time when you want to insert, at first, you add it at the very back of the array, is it? as the array. So that then you need to what? Then you need to keep checking with its parent node. Is it? And if it doesn't meet the definition, you need to do the swap. Is it? And whenever we do swap, it's in place swap. Is it? So that's why heap regarding this heap tree implementation, is it? It all just involve the array itself. So it's regarding in space, it's very efficient because you don't need some other temporary array to hold all the values. That is just the array itself, and you do everything in place. Okay. Okay, so what we just discussed is it, and you can add new items, is it? And after you add, you still need to do adjustment, is it? So all of this, basically, with heap insertion, you can build a minimum heap tree, is it? So this concept, a lot of time, we call it heapify. So to insert an item, a lot of people also call it the name heapify. So it's some insert, is it? Insert, and you build the tree, is it? That's how you build the tree, okay? And in our example, what we discuss is minimum, okay? So the root node then is a minimum, okay? And all parent node value is less than child node. And you can also do the other way, okay? Maximum heap tree. Okay, so this is the idea about how we do the insert, okay, how we do the insert. And then next, let's see some more idea. Okay. Tree. Okay, so we finished heapify, is it? And all of these discussions, let me clear this out. Okay, so all of these discussions can be used in a new kind of sorting algorithm called heap sort. Heap sort. Okay, and generally speaking, previously we learned quite a number of sorting algorithms. That some sorting algorithms, the time complexity is order of quadratic, and some it's n log 2n. That like a quick sort and a merge sort. And generally speaking, heap sort also is order of n log 2n. Okay, log 2n. And then how heap sort works? Is it how heap sort works? So how about let's still take a look at a previous example. Okay, so we have this tree built. Is it 0? Then that 5. And here we have 9. Is it? And then we have 6. We have 11. Okay. And we have 16. We have 7. And over here we have 20 and 25. Okay. And then we have this array. Is this correct? I haven't double checked. 6, 11, 20, 25, 16, 7. Okay, so sub 0, sub 1, sub 2, sub 3, sub 4, sub 5, 6, 7, 6, 7, and 8 as a corresponding array. It's all stored in an array, okay, in an array. And this is minimum heap tree, as a minimum heap tree. So how do we do the heap sort? Is it? And of course, when you want to sorting, it's going to be arranged in some order. But is this in the original? No. But the first number, definitely, is it the root node already in its location? Is it? Root node already in its location. Okay, so we don't need to worry anymore. Is it? Okay, so then how do we sort? So the idea is you can get this 0 out. Okay, so you remove the root. You remove the root. After you remove, then you need to bring something up. Is it? So you need to find between the two child nodes, which one is smaller? Is it? So then in this case, we can see it's what? It's 5. Is it 5? And then you swap 5 back to the tree. Is it? I swap 5, then you need to bring 6 up. Is after you bring 6, then you need to bring 7 up. Is it? Okay, and with this new minimum heap tree, you keep getting the root node. Is it? I get 5. I can remove it. As I remove it, then what? Then you need to rebuild the tree, kind of. You need to make it minimum heap tree. So you need to move the 6 up. So 6 up, and then what? You need to move 7 up. After you move 7 up, you need to move what? 16 up. After you move 16 up, okay, you get this new minimum heap tree. Is it? You can get the root number removed. Is it? And then you can repeat this process one by one each time. Is it? And then after you remove all the nodes, then the output is going to be arranged in ascending order or descending order. Is it based on how you build the tree? Is it? So you can see if we apply what we just discussed, you can sort all of the items. Is it? Whatever random order, you can sort them into ascending order. Is it? That's why we call this sort, because it's based on a heap tree, minimum or maximum. That's why we call it heap sort. Okay, heap sort. Okay, so the general idea then, how did you come up with the time complexity is n log 2n? Is it? And then think about the heap sort. Heap sort, the very first stage, you have some random number, random order list. Is it? Then you need to put them into a minimum heap tree. Is it? So that process, we call it a heap phi. As a heap phi. And the heap phi, its time complexity, and if you strictly analyze, it's quite complicated, and it's said it's linear. Okay, it's linear. And you may see that it's not, because it involves some Taylor series, okay? Because you need to insert, and then you need to also balance it. Is it? So overall, when you add all of them together, it's linear. Okay, but that doesn't matter too much. Okay, that's the first step. You need to build the tree. And after you build the tree, then it involves you remove item by item. After you remove an item, then it involves you need to bring some number from bottom to the top, is it? So it involves along your tree height, is it? Along a path. And the path basically it's some like a tree height. Is it a tree height? Depends on how many levels. Is it how many levels? And along one certain branch. Is a certain branch. So this process, we call it sift up. Okay, sift up, because you're going to move the number up. Is it one by one up, sift up? So it involves all of the numbers along the path you are going to move up, is it? And generally speaking, what we learned in a tree, binary tree structure, along a path, generally it's how many operations? It's log 2n. This is a tree height. Overall speaking, it's log 2n averagely, is it? But this remove involves what? Involve everyone. Is it? Everyone. So totally you have n numbers. Is it? So that's why the order is. Then for this sift up process, the delete, as we call it, sift up, involving this process, it's n log 2n. And you build the heap file as order of n, is it? And definitely this one is greater than linear, is it? So that's why we say, okay, heap sort, generally speaking, is n log 2n. Okay, n log 2n. And also if you read the articles about the comparison between because for n log 2n, we also learn quick sort and merge sort, is it? So among three, heap sort is the slowest, okay, because it involves like you build a tree, okay, heap file, and then to sift up, okay. So it's a slow, but its advantage is the store you using array, okay, and it's in place storage. Okay, so the space efficiency in this regarding heap sort has some advantage. Okay, so anyway, each one has their own advantage. So this is the general idea about heap sort, okay, heap sort. And basically heap sort involves you delete for one by one from the minimum or maximum heap tree, okay? And we call that procedure sift up or some other name, okay, some other name. So this is regarding heap sort. And in Java previously we learned, so you may ask where heap sort is applied. Is it Java priority queue? Priority queue, it's even though it's first in, first out, but it's based on priority, is it? And because it involves priority, so you need to do sorting, is it? How you are going to do sorting? So it use heap sort. So it's minimum heap tree. So that's what it implements for the queues priority arrangement. Okay, arrangement. Okay, so this is the concept for heap sort. Okay, heap sort. So we can let me probably write it down. Okay, heap sort. Okay, heap sort, generally speaking, it's the order of n log 2n. Okay, the time complexity. Okay, so how do we do the heap sort? The procedure, the algorithm is you first turn a collection to a, in our case, minimum heap. Okay, you can also, if you want to descending order, you can arrange as maximum heap. Okay, then what we want to do is, I just discussed the conceptually. Okay, and how we implement using array. Okay, using array, and the idea is like this. Then it's going to repeatedly. It repeatedly says swap the first one with the last one, so that we can decrease the range. Okay, to decrease the range in heap. Okay, in heap, and each time is by 1. Okay, because you're going to remove that item. Is it? You're going to remove the item, and what we are going to do is we are going to sifting the we are going to sifting the new first one into its position. Is it? You remember we do the sift up. Is it in heap? Okay, in heap, and this will continue. Okay, continue until the range is 1. Is it? Then you are done. Okay, then you are done. So this is the general algorithm for the heap sort, and visually we also just sort it. Okay, just sort it. So let's see. Let's see if I can use what our example just discussed. Is it just discussed? And first, how about let's see. So that's the heap sort. Conceptually and visually, we already know how to do it. Okay, so how about let's just take a look. So what I'm going to do is, let's see, first, how about, let's repeat this so that we first understand how do we do the rearrangement. 5, 6, 9, and then I have 16, I have 11, I have 20 and 25, is it? And then I'm going to have 7 here. Is it? 7 and 0 here. Okay, 0 here, and 7 and 0 here. And for the array part, then what it looks like, it's 5, 6, 9, 16, 11, 20, 25. 7 and 0. This is array. And suppose you want to insert 23. Where do you think you should we should insert 23? And first, first, let's see. Let's see this. I messed up here. Okay. Let's get rid of this part. Let's get rid of this part because this is not balanced yet. Okay. And first, we have 7 added. Is it? We have 7 added, and what should we do after we add 7? this is not a minimum heap tree yet, is it? So we need to swap this two, is it? So this is going to be 7 and this is going to be 16, is it? So 7 and 16 need to be swapped. 7 and 16, is it swapped? And then we want to add 0. The 0 I initially inserted here. Is it insert here? But that won't work. That's not a minimum heap. So we need to keep swapping. So here is 7, here is 0. And then we need to swap. So 6 and 0. And then swap. So 5 and 0. Is it? So so how about let's rewrite this array, okay? So 0, then 5, 9, is it? And then we have 6, 11, 20, 25, 16, and 7, is it? And then 23. So now we want to insert 23. Where do you think we should insert? We just insert in array, we just add it at the back, is it 23? So it's going to be the left child of 11, is it? And is this going to maintain the minimum? It's going to maintain, is it? So you don't need to change, is it? We don't need to change. Okay, and then the idea is if we go back to see what over here it says, okay. And here, when we do heap sort, this part already done, is it? So this heap 5 part is already done. The tree we already built and it meets the minimum heap tree requirement, is it? And what the second part means is you're going to keep doing kind of remove, is it? And you cannot just do remove, is it? After you remove this item, is it? So 0 out, is it result? And you remember we are going to do something on the tree, is it? We are going to do something on the tree. But how that works for this array, is it? The idea is how do we deal it with the array? Because when we implement, we work on the array. Is it? We are going to work on the array. So we get 0 out. And the algorithm, what it says is it's going to swap the first with the last, with the last. Okay, and then what it says is shift the new one, okay, into its position. Into its position. Okay, so what that means? So what that means, you're going to basically kind of take off 0. Is it? Take off 0, then swap the first and the last. Is it? So you already remove it. You're going to bring the last here. So you're going to bring 23 here. So basically, your range decrease by 1. Is it? Range decrease by 1. Is it? Your range decrease by 1, but this is not a balanced one. Is it? Basically, you are going to, if we take a look at the tree, what happens with the tree is this is already gone. Is it? And you are going to let me use erase. what you're going to move 23 here. Is it? You're going to basically get rid of this branch. Is it? Get rid of this branch. But is this a minimum heap tree? This is not a minimum heap tree. Is it? So it's the same thing. You need to rebalance it. Is it? How you're going to do it? You're going to compare with the smallest of its child. Is it? So 5. So you need to swap it. So 23 and 5. So here you're going to swap this to 5 and then you move it to 23 here. 23, is it? And then next you're going to compare with the minimum of its 2 children. Is that it? Oh, I'm sorry. After we delete 23, after we did, there is a problem here. Is it? Because this tree itself is not balanced. Is it? The tree itself is not balanced. So how about let's go back. So if we take a look at both the tree and the array, okay. So how about, I forgot that step. So it's, so how about let's clear this out. So that let's reset as, let me redraw that tree. Okay, that tree, hold on. It's a little bit of mess. I have 0, is it? We have 0, then we have 0, then we have 5, 9. 5, 9. That's in the right location. Is it? Then I have 6. I have 11. 6, 11. Then we also have 16 here. 16 here, 7 here. Is it? And 23 is here. Is it? And then I have 20 and I have 25. Is it 25? Okay, and then we have our array looks 0, 5, and 9. Is it? And then we have 6, 11, 20, 25, 16, 7, 23. Is it 16, 23? Okay, so then let's see. So we are going to remove 0. Is it? We are going to remove 0. So 0 is removed. Is it? And what the algorithm said, it's going to bring the last one to the first. So 23 is going to be here, is it? And 23 is gone. And your range is decreased by 1, is it? So 23 is going to bring back to the top, is it? So now we have this tree, is it? But this tree is not the minimum heap tree, is it? So we need to keep do swapping with the smaller one between its 2 child. So 5 is smaller, is it? So we are going to swap 23 with 5. So 5 and 23, is it? 5, 23, and you need to implement it in array, is it? So you are going to bring it to 5 and 23. Is it over tree? We understand, but when you do the program, that happens in array, is it? And we said it's everything for heap sort, it's in place, is it? It's in this original array, okay? And then you need to keep compare with its child, is it? And it's greater than the child, so you are going to swap, is it? And the swap is 6 and 23, is it? So what else? You need to swap these two. So this is 6. This is 23. Is it? And what next? You need to find the less of the two. So this is a child, and it's less than, so you're going to bring 7 up, and 23. Is it? So 23 then need to swap with 7. Is it? So 7 is here, and 23 is here. Is it? 23 is here. So now you have this balanced. Is it? So that's what the algorithm said. After you remove the top, is it? Remove the first one, because the first one is always going to be the minimum one. But all of the remaining, it's not guaranteed. Okay, it's not guaranteed that it's going to be in its order. Okay, let me rewrite. This is going to be 23 because otherwise mess up. Okay, and then your range is going to be reduced by 1 after you remove one item. Is it? And we call this whole procedure sift up. So you remove one, and you also need to bring things from the last, so it's at the bottom up. Is it? So we call it, and then you need to rebalance. So that's why this is sift up. Okay, sift up. And then you are going to apply it next to this range. Is it? So you are going to remove 5. So 5, you add it to the sorted list. Is it? So 5 you remove. Then what you need to do, same thing. You need to bring this 23 up. Is it? So now your range is going to be shortened by another 1. Is it? So 23 is here. After you bring 23, then we need to do the same thing. Is it? Have I already removed 23? I think I did. Is it? I did. And then how about let me clear that? Okay. Kind of. Messy, is it? Okay, so we have the 23 here. 23 to its, we swap with the first, is it? But this is not balanced, is it? Not meet the minimum heap requirement, is it? So same thing, then you need to swap with its child node, is it? If the child node value is smaller than the node itself, is it? So you can bring 6 up, is it? So then 6, 23, and then same thing, is it? 7 and 23, is it? So, and then 23 and 16, is it? So 16 and 23, is it? So, so you're going to keep this swapping, and you get 6, the minimum one at the first. So next you can remove this 6, and then you need to bring the top, bring the bottom one back to the first, and do this again, and then. So each time after you remove, you always need to maintain the minimum heap tree requirement. Is it? And how do we do that? It involves the array. We move around the elements. We do the in place swapping. Okay, so all of this concept is regarding heap sort. Okay, so the second phase is sift up. Okay, and you can kind of go over it after class in detail. Okay, so that's the concept. And then what next one, let's check about this couple of questions, okay. So then regarding the minimum or maximum, so it doesn't matter, heap tree, is it? Anyway, it's a complete binary tree. Okay, complete binary tree. And so here, then the question is, can you determine totally, okay, the minimum and the maximum number of elements for a complete, okay, complete binary tree with height with the height of h, suppose. So how do we determine this? Just think about it. What will be the minimum and maximum if suppose a tree, the height is h, the tree's height. So how about let's draw it as it's kind of look like this. Is it? And we know this is level 0, this is level 1, this is level 2, is it? And the height of this tree is 2, is it? And you have 3 levels, is it? 3 levels. So what's going to be the maximum number? Maximum now is this case. It's the complete one, is it? Every leaf node also filled. And then let's see how many nodes you have here. Okay, total is regarding the tree. How many? You have 2 to 0. Is it? How many nodes you have here? It's 2 to the 1. Is it? You have 2. How many you have here? It's 2 to the 2. Is it? So if you have height h, what is that going to be? That's going to be 2 to the h. Is it 2 to the h? So what's going to be the maximum? It's going to be, you need to add all of them together. Is it 2 to the 0 plus 2 to the 1 plus 2 to the 2, all the way to 2 to the h. Is it? So it's a summation of some geometric sequence. Is a geometric sequence. And I don't remember what the formula is. Okay, is it a1 minus an 1 minus a something, the geometric sequence? So from your math, is it? And anyway, so you can find the summations, you follow certain formula, is that we can find the total number. So this is the maximum. And what's going to be the minimum case? The minimum case, then it's going to be what? Then you don't have all of this, is it? So at the very bottom, how many you have? How many you have? You have the very bottom is going to be 2 to the h. Is it 2? Basically, you only have 1. Is it? You only have 1. And it's what? It's you minus 2 to the h minus 1. Is it? So what is the minimum? The minimum basically is going to be 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the h. The last level is it's going to be minus 2 to the h minus 1. Is it? So basically it's what? It's from 0 to 2 to the h minus 1 plus 1. Is it? So that's going to be the minimum number of values, items you can have for a complete binary tree, okay? So this tells us the relationship. If you know a tree height, is it, then the minimum and the maximum number of elements that it can hold, it needed to meet these two requirement. Okay, these two requirement. Okay, so this is a some side concept. Okay, and what is the next one? So over here, I just want to. So let's just reverse our mindset. Okay, consider maximum heap. Okay, maximum heap. So if it is a maximum heap, then my question is, do you think, how do you know if this is going to be? So I have an array stored like this, 23, 17, 14, then 6, then 13, then 10, then 1, and then 5, then 7, then 12. Okay, so I have this sequence. This is a sequence. So my question is this sequence a maximum heap? So if I just give you this sequence, is it already in a maximum heap? So how do we determine this?
Well, no, it is not. It should be the sum of powers of 2.
It's no, I mean, this maximum heap, it doesn't mean the total number. I mean, is this arrangement in array going to be a maximum heap tree? Does it follow the maximum heap tree? How do you determine it? So how about, anyway, it's close to the end of the class, okay? So how about we can discuss this tomorrow, or not tomorrow, Thursday class, because we haven't got to the coding part. So Thursday, we are going to discuss the coding also, okay, regarding heap and heap sort. Okay.
It looks like it's in the correct order.
Pardon me?
It looks like it should be in the correct order.
It looks like? But not looks like, you need to prove it to me. Is this
Would
going?
you like me to walk you through it then? Or?
Yeah, so you want to get it done today? Okay, so how do you work through?
So 23 would be the root.
Okay.
And then 17 would be the left child and 14 the right child.
Okay.
6 would be 17's left child and 13 would be 17's right child. And then 10 and 1. And then 1 and 5 on 6 and 7 and 12 on 13.
5 and 7 and then 1.
Yeah. And then 12 on 13.
Yeah, so if you check everything, does this meet?
The 7 is correct, right?
Yeah, so is there a question here?
Yeah, 7's wrong.
Yeah, okay, so this is not, is it? Yeah, so if you just check here, it's not easy, is it? But once you have this tree, then it's easy. But just visually, you can see the tree, is it? But in your program, you don't have a tree. You only have an array. Is it? You only have the array. So how do you check? Then you need to use the index to do the check. Is it? So that's the idea. Is it? Because all you stored is those array and the index. That's all. You don't have this tree. Is it? So you need purely based on the index to find its child node and then to see if it meets the condition. That's the idea, okay? Okay, so anyway, so today we kind of get the concept part, okay, of the heap sort and the
Question.
heap tree. Yeah, please.
My question is we were removing nodes from the tree. Where were we
Yeah.
putting them once they were
Yeah,
removed?
because after all, you are going to have the sorted result. So you put it in either if you want to have an array, any kind of data structure, linear data structure. Yes.
So we're creating a sorted list
Yes, yes,
and we're
yes,
just moving it over to there. Okay.
yes, yes, yes. Okay, so so that's all for today. Okay, so tomorrow we are going to go to the coding part. Not tomorrow, Thursday. So see you. Bye.
Bye-bye.
Bye.